Right, and the last but not least talk will be on SLING, using dynamic analysis to infer program invariants in separation logic, and it will be given by Chen.
Thank you for the introduction. So my name is Chan. Today I'm going to give a talk about SLING, a dynamic analysis technique to infer separation logic invariant for Heap-based program. So this is a joint work with Gu Longzhen and Tan Vu Nguyen. So our motivation for this work is come from the fact that understanding or debugging program is hard and tedious, but we all know that program invariant can help. So by definition, a program invariant is a property that always holds whenever program execution reaches a specific location. And here I can list some other use invariants like proving program correctness, documentation, maintenance or program-based security analysis, and so on. In particular, for Heap program, we can use invariant in separation logic. And this is a short introduction about separation logic. Separation logic is a compact and precise presentation for local reasoning of Heap program. And there are two important features of separation logic. First of all, is the separating conjunction to indicate the disjointness between heap region. And the second one is the inductive heap predicate to model inductive data structure. So first of all, in this slide, the DDLL predicate here model doubly linked list segment with the head and the tail node, with the head and the tail node, and as well as the previous node and the next node of the whole data structure. And in this definition of DLL, we also use two other kinds of predicates that are M to indicate the empty heap, and the point2 predicate to indicate the single memory heap. So let me give an example how is and what is separation logic invariant for Heap program. So on your left-hand side is a concat recursive method to do the concatenation of the two doubly linked X and Y. And your right-hand side is the specification with free and bool condition for this method. And this specification is non-trivial, given the fact that, for example, it uses the separating conjunction in the precondition to denote the disjointness between two inputs here, two inputs doubly linked X and Y, to avoid the possible cycle in the result. Moreover, it requires that the next node of the DOL is new so that the base case of the recursive method is reachable, and on the other hand, it requires that the previous node of the DLLY is also named to avoid possible memory leak happen when we do the update on the previous field of the Y doubly linked. For the bool condition, we will see the update on the next field of the doubly linked X and the reverse field of the doubly linked Y to indicate the connection between the two leads in the result. So the question is that how can we infer such non-trivial separation logic invariant? So there are two main techniques here. First of all is a static analysis. This is not that a sound technique, but it is expensive and may be limited to simple form of invariant. Another technique is dynamic analysis, which can analyze just a finite small set of execution traces so that it is efficient but unsound in general. And in this work, I'm going to I would like to introduce SLING, a pure dynamic technique to infer separation logic invariant. So this is the overall structure of our tool, of our technique. So the input is a program C, a set of predefined predicate P test suite and the location L that we need to infer the invariant. And the output is a list of candidate invariant as the location L. So there are three main components here. First of all is the model collection to collect the, to run the program C under the test T and collect the model, the offshore model as the location L. And then the main component infer invariant will take the Z model and derive the candidate invariant, and then we also have the validation on the validity of the invariant. So the general invariant template here is a separating conjunction of a list of atomic heap bracket as well as a pure constraint with a conjunction of equality constraint over pointer variables. So in the first step, model collection, we use a debugger to set a breakpoint at L and then run the program, collect the set of stack heap model whenever the breakpoint at L is hit. So first of all, in the concat method here to infer the precondition and the bool condition of concat method, we annotate relocation L1 for precondition and L2 and L3 when the method return for the bool condition. And for just a single input, on your left-hand side, we can collect some traces, some model as the location L3. Note that just because the concat is a recursive method, so with just a single input, we can observe many traces at one location. And for the inference, so the main idea of the inference is that we will split the model that another name traces snapshot connected as a location L into sequences of subheap. And for each sequence of subheaps, we infer an atomic heap bracket that is satisfied by all subheaps. So this is the refinement iteration process. So through all the stack variable of the program, and we to split a heap into subheap, we use a defuser to find the subheap containing all memory cells reachable from a root pointer up to a boundary that are the new pointer or the stack pointer variable. So the insight here is that the subheap are small to model by atomic heap bracket, and the common boundary between the subheap will be the argument of the atomic heap bracket. So first of all, here in this, we show the subheap on three traces with the root pointer x, and the common boundary of x among the subheap will be x, nil, and 10. So now we will search for atomic heap brackets certified by all the root subheap. The first kind of atomic heap we try to infer is an inductive heap bracket. We will list on possible inductive heap bracket template in which have at least one parameter has the same type as the root pointer and argument chosen from the common boundary of the subheap. And then we use a separation logic model checker to select predicates certified by all subheaps. So first of all, with the given subheap of X below, we choose some candidate in string here. So in particular for this predicate, the separation logic model checker can check that all subheap are sacrified third predicate, and the model checker also gives us the instantiation of the existential variable in the predicate. And then we also infer silicon heap predicate if we observe that every root subheap has only one single memory cell, or the M predicate when every root subheap is empty. So next step is that we will try to infer some equality constraint over two different pointer variables, include stack variable, existential variable, nil, and as well as a special variable for return value if we want to infer the bool conditions. So from the combination between the stack and the instantiation of existential variable, we we observe, we can infer some equality constraint like the return value equal to x and the existential variable u2 equal to x. And we continue the process on the order stack variable like temp or y, and we got the final result as a location, one of the final result as a location every here. And after the simplification, we can get the a prime every here. It's interesting because and expected because the first two predicates so that act a list segment to y, and from the parameter of the last two predicates, it shows the concatenation between x and y. For the other location, we also have some result like for recondition as a location L1 and the other both condition as a BK L2. And now we want to validate our result to remove spurious result. So we use a frame rule observation logic at a large way validation to remove spurious result. Given the fact that if we have a free invariant and a both invariant of a curve C, then if we add the same frame R into them, it's still a valid pair of free invariant and the both invariant. So first of all, given the precondition at L1 and two possible solutions for the both condition at L3, we can check among the frame rule over on the observed subheap. On the observed stack heap model, and for the pair of F1 and the first solution at F3, we see that it follows the frame rule for all the traces. However, for the second solution at L3, F2 here, it doesn't follow the frame rule as a second trace. Furthermore, here it said you can say that you can see that the residue heap, the frame outside of the green box here are different, so that they are mismatched. So to evaluate our technique, we implement the tool in Python with the LLDB debugger for C program, and we use it as the underlying solver. Note that we can handle all the programming languages using the right debugger, such as CDB for Java or PDB for Python. And for the benchmark, we use a VC triad benchmark with a concept of 157C heap program in 22 categories. And we also use the annotated verified specification as a route tool. And we want to clarify that mismatch infer invariant do not imply that the infer invariant are bad. So I have a very big table here, and I won't go into the detail. You can find the detail in our paper. But the summarized result is that our tool can infer the desired invariant for more than 100 programs, and for 40 programs that our tool cannot handle, there are 5 buggy programs, so that we cannot obtain the traces. There are 15 program, so that's the location that we want to infer the invariant are unreachable with a random input. And there are 3 programs that we can generate the loop invariant due to the large traces and overwhelming G3. And for the last 17 program, we get the invalid traces from the debugger because for some memory reasons that already free, but the debugger is still report them after the free segment. We also compare our result with a static inference tool S2, and our experiments so that the result of the two tools are comparable. So now I want to discuss a little bit more about the use cases of the Infer environment. We can use the Infer environment to explain input, to explain bus. So given input that read buggy location, our tool can discover environment so in the unaffected result. And third environment helps the developer to analyze the bus. The second use of the Infer environment is identify spirit one name from a static tool like Facebook's Infer. So using our Infer environment, we can confirm the spirit one name from Facebook Infer in a program. And for the SC order location, the Infer environment also confirms the error. So for the filter work, there are a couple of filter work here. So we want to reduce the subspace for efficiency of the tool. And we also have a score system to run the Infer environment to solve the U4 environment first. And we also want to support arithmetic property of the data structure such as size or the sortedness. And more importantly, we also want to use an automated verifier to validate the Infer environment and also use a counter example from the verifier to generate new test cases and refine the result. To conclude, in this work, we introduced SLING, a pure dynamic analysis technique to infer program environment in separation logic for heap program. Based on the insight that the heap as a program location can be partitioned into disjoint regions which are reachable from various stack variables, and the region can be modeled by atomic separation logic formula. Some interesting technical detail here. So we find and use boundary variable to instantiate predicates. We use a separation logic model checker to compute both instantiation for existential variable and residue here. And we use a frame rule of separation logic to validate the Infer environment. And for the result, our experiments show that our tool can discover useful environment over a wide range of data structure of non-trivial program. And our tool is available online. You can try it. Thank you, and I'm happy to take the question.
Hi, great work. So I had a question. As far as I understand in your work, the definitions of the inductive predicates have to be provided by the user.
Yeah.
But do you have any, and obviously inferring those is a very challenging problem, but do you have any thoughts or ideas for how you could extend this to infer definitions of inductive predicates, let's say given the C definitions of like data structures?
I see. Yeah, a good question. That we also plan to do that. First of all, we can infer some heap predicate from the definition of the memory. So first of all, in the doubly linked list node here, we observe that there are two fields, NAC and previous, and we get that it should be a doubly linked list. And another kind of another way of infer the inductive predicate is based on the program structure. So first of all, if it's a recursive program following the NAC pointer, so it's possible that the NAC pointer point to the same data structure, so we can construct the inductive predicate like that.
Thank you.
Thank you for your talk.
Thanks.
I was just wondering what the most complex data structure that you discovered a predicate for was. So in other words, red black tree or some complicated heap structure. Just curious.
Yeah, actually, in our current work, if the user can provide us the predefined heap predicate, we can infer whatever data structure is. So for example, here we can infer doubly linked, circularly, priority tree, red black tree, and so on. Yeah, but if we want to infer the heap inductive predicate, automatically it is more challenging for those data structure.
Thank you.
Thanks.
Hi.
Hi.
Are there any guarantees that you can provide in terms of the learned invariant? Is it like if you use DICON, it'll typically tell you that it's the strongest invariant you could find? Is there any other, like any guarantee?
Yeah, currently there are no guarantee like that, but it should be our future work. When we iterate, we use static verifier to do that.